Hi everybody and welcome to the 12th video in the series TensorFlow Basics with Hemant, and that's me. In the last video we discussed about Keras loss functions. We also discussed and compared various Keras optimizers, and we also talked about Keras tuner, right? So throughout the series we have been through the processing of the data till the training of the model, and we also saw like how to get predictions out of it. What we are going to do today in the today's video is we are going to be discussing about the distributed training, right? So far we were training the models, but we were training them on a single machine and a single CPU or a GPU which is available, right? But we'll see what is the need for the distributed training and various aspects related to the distributed training, like the concept of the model parallelism and the data parallelism, and synchronous and asynchronous distributed training, what these are, and how distributed training is supported in TensorFlow. So what is the API in the TensorFlow which can be used to do the distributed training um, on a multi GPU machine as well as multiple machines which are having multiple GPUs. Okay, so very interesting topic. Let's go ahead and get started. Okay, so let us understand a few concepts to begin with. So let's first discuss about the model versus data parallelism, right? So there are typically two ways to distribute computation across multiple devices, right? So let's say if we have very large data sets, right? And we want to do the training of the model with very large data sets, then what we have to do is we have to spread the computation across multiple GPUs and maybe potentially across multiple machines also, right? So there are two ways to it. One is we can split the data itself. That means let's say if we have 100k records, then we can like spread the records across the GPUs. So if there are multiple workers, so worker could be like multiple GPUs across multiple servers or multiple GPUs just on a single machine also. So what we do is we partition the data, we slice the data, and we give the data slices to each individual worker. And once the computation, that is the gradients, are calculated, actually they are kind of aggregated. Okay, aggregated back, and they could be aggregated back in multiple ways, so we are not going into that just now. Okay, and then there is a second way which is called as a model parallelism. So in the model parallelism is what happens in the model parallelism is we have a shared data and we are splitting the computation. So for example, if the model is consisting of multiple layers, then what we do is we kind of do the computation for say layer 1 here, layer 2 here, and layer 3 here, or maybe we can do layer 1 and 2 here, and 2 and 3, 3 and 4 here, and 5 and 6 here, right? So we use the shared data and do the spread the computation across multiple parallel workers, and then we basically use those gradients which are computed by the different layers. We kind of aggregate those and use those. But from the TensorFlow perspective, most of the strategies, in fact all the strategies that we come across on the TensorFlow, they basically use the concept of the data parallelism. That means a single model, the whole model is replicated across multiple workers, and that worker could be just a single, like worker, as in the TensorFlow terminology, worker is fundamentally a machine, right? And that machine can have multiple GPUs. But from the computation perspective, if you really see, they are basically the GPUs, and they could be like on one machine or multiple machine. So what we do is actually we have a full model kind of replicated on all the GPUs, and then we split the data and give it to those GPUs, and then we do those computations on the given set of data, and then we aggregate them, right? So the takeaway, two fundamental ways of doing the distributed training: data parallelism and model parallelism. And as far as the TensorFlow goes, we are mainly going to focus on the data parallelism. Okay. Now there is another concept involved here, which is synchronous and asynchronous training. So in the synchronous, so there are two common ways of distributing the training with the data parallelism, right? So we are using the data parallelism, so, and under the data parallelism we have sync or async training. Okay. So all workers in the sync training, all workers are going to train over different slices of the input data in sync and aggregating gradients at each step. So for example, if you have GPU 0 to GPU 255, GPU 0 to GPU 255, then each of them is going to calculate the gradients, and then it is going to be synchronized. Now how it is synchronized? There are certain algorithms for synchronization of the data across the multiple GPU, and typically the sync training is supported via all reduce algorithm actually, and the async training is basically supported to the parameter server architecture. Okay, so in the synchronous kind of algorithm, what is going to happen is the gradients are basically calculated individually by all the GPUs, and then they are synced up with each other, right? So there is basically an algorithm which is going to update a new model when everybody, all the GPUs are finished. The gradients are kind of synced up, and then they are basically given to all the GPUs once again. Okay, the gradients across all the GPUs, they are going to be synced up before the next batch begins. Okay, so that is a synchronous training, right? And normally the protocol involved here, especially in the TensorFlow, is NCCL. Okay, so there is a protocol which is called as NCCL, which is used for syncing all the gradients across all the GPUs. Okay, and then in the async training, what is going to happen is, if there, let's say there are multiple GPUs, they are going to be conducting their training independently, and what they are going to do is they are going to send the gradients, and then they are going to pick up the new model automatically. They are going to download the new model automatically, and that process, so they are not going to wait for any other GPUs to finish, etc. They're just going to send their updates, get the kind of the latest model, and go ahead with the next batch. That is what the asynchronous training is all about. Asynchronous training is all about. And then there is a concept of a parameter server. So there is a server which is going to hold the parameters in the async kind of algorithms. Okay, so under the data parallelism, basically two methods of training: synchronous and asynchronous, right? And synchronous training is supported via the all reduce algorithm, async to the parameter server architecture. These are the key takeaways. Okay, we are not going into the details of the algorithm and how exactly it works, but from the like, if you at the highest level of understanding, under the data parallelism we have sync, async, and async is basically all reduce algorithm. Sorry, the sync is the all reduce algorithm, and async is the through the parameter server architecture. Okay, now how does it work? A little more different view of the sync strategies is, this is how it is going to look like. So we have GPU 1, 2, and GPU n, and then what is going to happen, the gradients are going to be fed back. They're basically going to be a kind of aggregated, and a mean is going to be found, and then there's going to be an updated the gradients here, and then they are going to be kind of synced up with everybody here. So there's a sync here, and then there is a sync here, right? Now in terms of the actual implementation and the API from the TensorFlow perspective, there is API called as tf.distribute.strategy, and that's a TensorFlow API to distribute training across multiple GPUs or even multiple machines or TPUs also. So GPUs and TPUs both are supported by this particular strategy, this particular API. Okay. The good thing is the tf.distribute.strategy can be used with high-level APIs like Keras, so that's a good thing. It's going to simplify the programming for us, and it can also be used to distribute custom training loops. So it is going to work with the different mechanisms in the TensorFlow. Like even if we are doing the custom training loops, this particular API is going to work. Okay, so under this tf.distribute, we have tf.distribute.mirrored strategy. So this strategy is basically for synchronous distributed training on multiple GPUs on one machine. Okay, so multiple GPUs are supported, but they are restricted to one machine, right, under this particular strategy. And since it is a synchronous, as we discussed earlier, it's going to use the all reduce, and it is going to aggregate the tensors across all the devices, and it's going to make them available on each of those devices or the GPUs. So when we refer to the devices, it means GPUs in this particular case. Okay. Now in terms of the distributed training architecture, the TPU strategy is same as the mirrored strategy. So only the implementation is going to be a little different to support the TPUs. Okay, and third one is the tf.distribute.multi-worker mirrored strategy. Now in this case, it's once again synchronous distributed training, but multiple workers. So multiple servers are supported, and each of the servers could have potentially multiple GPUs also, right? Now in terms of the synchronous training, there is also another strategy which is called a central storage strategy. Now in this case, the variables are not mirrored. That means we saw that, right, earlier, the variables were replicated, the model was replicated, but in this case they are not replicated. They are put on a single CPU, and the operations are replicated across all the local GPUs. Okay, so these are all the synchronous training strategies that TensorFlow is going to support, and we'll see the examples of this in a notebook also very shortly. Okay. In terms of the asynchronous, we have tf.distribute.experimental parameters server strategy. So this is an experimental API right now. So this is going to support the asynchronous training kind of type of algorithms, and basically there's going to be certain machines which are going to be acting as parameter servers, and multiple machines are also supported on this, and variables are created on the parameter servers, and they are read and updated by workers in each step. Okay, so we have a choice of synchronous and asynchronous type of algorithms and the strategies in the TensorFlow. Okay, now how is it going to look like in Keras? That is something which we'll take a look here. So first what happens is we create a strategy. So it's a very simple thing, tf.distribute.mirror strategy. This is just an example of creating a mirror strategy that we discussed in the earlier slide. So once we create a strategy, what we have to do in the Keras is we just say that with mirrored strategy dot scope, and then what we do is we create a model. right? We declare the model as usual, and we can declare metrics and optimizers and all that. And once that is done, we can just compile the model and then go ahead with the business as usual. So what is going to happen if we just say this mirror strategy, if we declare this model under the scope of this mirrored strategy or any other strategy, distributed strategy, then the computations are going to be spread across the multiple devices or multiple machines, right? So as you can see, there's hardly any change in the code, right? And that is the beauty of using the distributed training strategies with Keras, right? So it's very straightforward and simple, right? Now there is another thing that we should be aware of when we are talking about the distributed training. So there is a framework which is called as Horovod, which is basically a distributed deep learning framework. I think this is just a typo. This should have been O here. So Horovod is a distributed deep learning framework which is developed by Uber, and it supports TensorFlow, Keras, PyTorch, and Apache MXNet deep learning frameworks. So that is practically everything that we might need usually. And the goal of the Horovod is to make distributed deep training fast and easy to use. So fast and easy to use. That's why they are supporting all these different deep learning frameworks. So if you have written a code using Horovod, changing it even if you are changing it to use different deep learning frameworks shouldn't be that difficult. So I'm going to discuss like how to use Horovod with Keras. So usually these are the steps which are involved. So we basically install the Horovod to begin with, that is just pip install Horovod, and then uh, in the code we are going to do just we are going to bootstrap this hvd.init, and then there is something called as pinning each GPU to a single processor. So there's a little bit of code around this. Another thing to understand is since we are doing a distributed training, effectively we are increasing our batch size, right? So if you're increasing the batch size, we can also scale up the learning rate, right? So that is something which we need to take care of uh, when we are doing the distributed training. And we also need to optimizer into the HVD distributed optimizer API, and we'll see an example of this. There is also another step. So if you want to have any kind of callbacks, we can have here. And then we need to save the checkpoints only from the worker 0, right? So we do not want other workers from compute corrupting them. So we do not want all the workers to save the checkpoints. So that's why we need to save the checkpoints only on the worker 0. So that's pretty much about the Horovod. Horovod is an like an independent framework, but it supports TensorFlow, and it's a popular framework for distributed training, and that's the reason I kind of decided to include it into this discussion. Okay, so before we actually go into the summary, let's also have a quick look at the notebooks. Let me zoom it a little bit. Okay, 1 minute. I think. Yeah. So I think that's a good size. So let's get started. So initially we'll just quickly try to see how those strategies API look like. So tf.distribute.strategy, that's the API, and it supports training across multiple GPUs, TPUs, right, and across the multiple machines as well. So what we do, we basically import TensorFlow as usual, and once we have imported, now mirror strategy, as we saw, right, it works across a single machine, and multiple GPUs on a single machine, and this is the way that we instantiate this tf.distribute.mirror strategy. So our API has got I think our import is already done. So this is what I'm doing. Before that, just to make sure that you know what is our runtime. So runtime is already set to GPU, right? So if you see here, it has said that it is replicating the model onto the GPU. Now the thing is, since I'm running it on the Google Colab, you know, basically I'm using the machine allocated to this particular notebook, and this has got only a single GPU. uh, I don't think I have any control over you know, the configuration of that machine. But as you can see, you know, since we had selected GPU, it got kind of selected here for the training purpose. Okay, and then we can also do the selection of the GPUs also, so we can specify the devices also if there are multiple devices. So let's try to see how this is going to look like. So obviously, uh, you know, I don't think there's going to be multiple machines available on this machine on the notebook. So this may or may not work in this particular case. But if you have a machine which has got multiple GPUs, you have a choice to select multiple GPUs also. Okay, or the GPUs that you want the training to be performed on. Okay. Now for the multi worker mirrored strategy, this is how the API is going to look like, and we have got only single device here. Now for the multi worker mirror strategy, we also can choose the communication option. The communication option could be there are, like, you know, you can choose the ring, you can choose NCCL. So there are a couple of other communication options which can be selected here. Let's go to this. So this is fine. And then interesting thing, how to use it with the Keras model fit, because you know, we want to use the distributed training, that is all good, but we do not want to like lose the Keras API, the simple API to use. So the good thing is we don't need to do that. Do not need to lose our Keras API. The tf.distribute strategies work well with the Keras API. So this is how it is going to look like basically. So we create this mirrored strategy, and then with this particular scope we are creating a model. We are creating a very simple model in this particular case, and then once we have created a model, we are compiling it here, and that part is already taken care of. And then we can create our data set. So here we are creating a very simple data set, and we are doing the model.fit over here, and we are just doing the two epochs here. Let's see how does this whole thing goes, right? So this is how the you know, the training is going to be distributed. So once we have this model under the strategy, under the scope of the strategy, we can just go ahead and use the model.fit, model.evaluate as usual, no change, right? Beauty. The same thing, we can also generate our dataset using the numpys. So here we use the dataset API, and here we are using the numpy API, numpy to generate our dataset. Is the same thing, but we are once again using the model.fit over here. Okay, so that was one thing. And if you want to find out like how many GPUs were picked up by this strategy, we can just use this num underscore replicas in sync mirrored strategy dot to print the number of the GPUs which were selected. Okay. Second notebook, we will just try to see we like we'll try to use a particular data set here, which is the MNIST dataset, and we'll try to train a model. So we are just importing this TFDS and TensorFlow, and then we will import this MNIST dataset, and we'll train that using the mirrored strategy. Right, so we are just importing the dataset for the training purpose. Fantastic, that was quick. We are going to create a strategy here, and let's try to print. So we have got only one devices, but it's going to work even if we had multiple. And then we are just splitting the data here, and what we are saying is batch size per replica. So for each replica the batch size is going to be 64, and in this case the batch size is also going to be same as batch size per replica, because we have got only one device. But just to explain the concept, if you have multiple GPUs, then the total batch size of the training is going to be in multiples of the batch size per replica in this particular case. And here we are just scaling, kind of normalizing the pixels by dividing it by 255, and then we are just caching and shuffling the dataset before the training. And then with the strategy scope, we are going to create this model as usual, and then we are going to compile, and we will fit once it is compiled. As you can see here, the replicas are getting created. So if we do not use a strategy and a distributed training, you don't have this concept of the replica, right? It will just use a single device and do it for you. And the last step, model.fit, as usual, no change. And as you can see, the training is being conducted as usual. So as you can see from this, integration with the Keras actually simplifies the process of distributing the training across multiple devices, right? And multiple devices even across multiple machines. So for example, instead of mirrored strategy, if you are using the multi-worker mirrored strategy, it will distribute it across the multiple machines also. Obviously there's going to be some step for configuring those multiple hosts, so there's going to be a little bit of an additional code for configuring those multiple machines, but otherwise it's going to remain more or less similar, right? So we just create a strategy, and with that strategy, under the scope of the strategy, we create a model. Then we just compile the model as usual, and we just do the fit on the model, right? Pretty straightforward. Now, third notebook that we have is about the Horovod, the distributed training framework from Uber. That is something we saw earlier, and I'm going to be walking you through with the usage of the Horovod with Keras, right? So to begin with, if you want to distribute the Horovod across multiple GPUs, we just have to install the Horovod, something like this to begin with. So we are going to do that to begin with. So yeah, the other notebook is running, so let's go and terminate that. So that part is terminated. That is terminated, and now we can go and install the Horovod. This is going to take just a few seconds, so that's the reason I'm just thinking. So I'm going to pause it because this building of the wheels could take some time. Yes, so as you can see, we have installed Horovod successfully. It took some time to build the wheels. Actually, it took almost like 15 minutes for me on a Google Colab. It could differ for you depending on the machine that you guys are using. So just be a little patient while the installation of the Horovod is done. Okay. So once that is done, we can import the HVD, which is horovod.tensorflow.keras and TensorFlow as usual. So once our import is complete, this is we can initialize the Horovod, and then we are going to like allocate single process to each of the GPUs. So this is what that code is all about. Okay, and once again, the runtime here also is a GPU. I've just kept it as a GPU. And then we are going to get this MNIST data set. Okay, and we are going to shuffle the data set and batch the data before the training. So this is where like we are normalizing the pixels and we are casting the labels uh, as well. And then we are going to be creating the model as usual. So in this case, the model is created as usual. We are setting the learning rate. So depending on the number of the GPUs that we have, we can scale up the learning rate based on the number of GPUs. So HVD dot size, that is going to give us the number of the GPUs, and accordingly we can scale the learning rate. And then we are going to wrap our usual optimizer uh, into, so we are going to create an optimizer here using the learning rate as a parameter, and then we are going to wrap it in the HVD dot distributed optimizer, right? So there are a few parameters here, and then we are going to compile as usual. Okay, so let's do this step. And then there is this one callback. So broadcast initial variable states from rank 0 to all other processes, right? So we want the updated kind of gradients to be passed to all other processes. So that is what this is for, callbacks. So this is necessary to have this. These are like kind of optional callbacks that we have if you want to have the learning rate, warm up, callback, etc. Okay, and then this is where if you remember, we had discussed this earlier, like saving checkpoints only on the worker 0. So we are doing this check. If the HVD rank is 0, then only we are calling this, we are basically creating this callback over here. Okay, so we are doing these callbacks, setting this, and then rest is simple, like we just use the model.fit using the data set that we have created, and the number of steps per epoch, uh, it depends, like we are setting it to some number of steps based on the number of the GPUs. So say 500 divided by HVD dot size actually. Okay, so it is, and we are just using all the created callbacks here, and then we just train the model over here. Okay, so this will go on, doesn't matter. So we basically understood how to use the Horovod with Keras, and yeah, it has got its own way of doing a few things, but more or less it's fairly straightforward. And as we discussed it earlier, it can be used with TensorFlow, it can be used with PyTorch, Apache MXNet. So that's a good thing about Horovod, right? So let's come back to the summary that we have, and just discuss what we learned. So what we discussed, we saw that if you have large data sets, and if you want to reduce the amount of the time it takes for us to train our models, we need to go for the distributed training. So distributed training is about spreading the training process over multiple devices, that is GPUs, over the single machine or multiple machines, and then we have the choice of using sync or async type of algorithms. So under the synchronous, we have mirrored strategy, which is a single machine multiple GPU. Then we have multiple machine multiple GPUs, multi-worker mirrored strategy. Then we have central storage. We really didn't discuss too much about this, but it uses a CPU to store the parameters which are getting updated, and then we have parameter server type of strategies also, right? And then we also saw how to use these strategies with the Keras. So what we do, we create a strategy, and within the scope of the strategy we create Keras model, and then we compile it and use the model.fit method as usual. And we also saw how to use Horovod specifically with Keras. So it's a fairly straightforward process, and that's that's all that we learned into this particular session. I hope this was helpful in understanding, at least at a high level, how the distributed training is being handled in the TensorFlow, and also using Horovod with an interface to TensorFlow and Keras, right? So I hope this was useful to you, and with that I will end this session. If you have any comments, any feedback, please let me know through the YouTube or through the LinkedIn, and I'll be back with another video shortly. Thank you so much.